Hi everyone, good afternoon. We welcome you to the knowledge session of Akka Streams presented by Anshika and Purva. And the topic for today's session is Akka Streams. So, before we start with the topic, let's learn some knowledge etiquettes. So, lack of etiquettes and manners is a huge turnoff. So, we should always try and follow the knowledge etiquettes. We should be punctual in our session and we should join the sessions 5 minutes prior to the start time and so that we can conclude on time as well. Feedbacks, so it is important to share the constructive feedbacks to the presenter so that they can improve and do better in their next session. And we should always be on mute while attending the virtual meetings so that it will avoid the disturbances, and we should avoid any chit chat that is not required in this session. Purva?
Yes. So moving forward, let's see our agenda for today's session. We will be covering the following topics today: why Akka Streams, Akka Streams Primer, Graph DSL, integrating Akka Streams with actors, fault tolerance and error handling, and finally a short demo. So moving forward, first topic is why Akka Streams. So our goal for the session is to learn how to understand, read, and design asynchronous, back-pressured, incremental, potentially infinite data processing systems, which are known as reactive streams. So reactive streams is basically an initiative that is started by the companies and team of engineers throughout the world. And this specifies the behavior of asynchronous back-pressured streams. To understand reactive streams, we need to have a understanding of few of the concepts. So reactive streams includes various components. The first one is a publisher, which is a component that emits elements asynchronously. Then we have a subscriber, which receives elements. And finally, we have a transformer. We call that a processor. And in reactive streams terms, which transforms the elements in between publishers and subscribers. Now, the whole point of reactive streams is that all the data that flows from publishers to processors to subscribers is done asynchronously. And we all know what asynchronous means. So, but just to refresh, an asynchronous operation is basically it is evaluated or executed at no well-defined time, and this is done without blocking any running code. Now, one thing to note about reactive streams is reactive stream specification is not a user API. It's more of a service provider interface, SPI. What that means is that the reactive stream specification defines the concepts and how they work, including the protocols between all these components. But the libraries that implement the reactive stream specifications have the power to choose their own API. And that is our focus. So we'll be learning how to use the Akka Streams API and what are they basically. So the Akka Stream API, it allows us to easily compose data transformation flows from independent steps. Moreover, all the processing is done in a reactive, non-blocking and in asynchronous way, which we have already seen what asynchronous means. So let's look at Akka Streams, and we are going to start with the components of reactive streams from the Akka perspective. So the first component that we have seen in reactive streams was publisher. So the equivalent of publisher in Akka Streams is basically called a source. So it is the entry point to processing in the Akka Stream library. We can create an instance of this class from multiple sources. It means that the source emits elements and it does so asynchronously, and it may or may not terminate. Then we have the equivalent of a subscriber, which in Akka Streams, which is known as a sink. So it means that it receives the elements when we are building a flow. It is not executed until we register a sink operation on it. It is a terminal operation that triggers all computations in the entire flow. So now in general, async will not terminate unless async will not terminate unless the publisher terminates. And then finally, we have the equivalent of the reactive streams processor, which Akka calls flow. It means that this flow transforms elements, maybe even their type as well. It is the main processing building block. every flow instance has one output and one input and one output value. So all these components are usually based on actors, and we build reactive streams by connecting all the three components. So now let's understand two concepts, which is known as there are two directions in Akka streams. The first one is called the upstream, and that basically means that towards the source. And the other one is known as the downstream, which is the opposite of upstream, and that means to the sink. So now let's move forward to Akka streams primer. So it basically includes 3 points: materializing streams, operator fusion, and async boundaries, and finally back pressure. So materializing streams. So the goal is here is to learn how to extract meaningful values out of the running of a stream. So with Akka streams, when you type components in a graph, something like source via some kind of flows to some kind of sync social graph, the components are static. They don't do anything. So they don't flow any kind of data until you trigger the run method on a graph, which we'll be seeing in the demo as well at the end of the session. Now, calling the run method on the graph is an expression, and it returns a value. And it turns out that we can obtain meaning from this value. This is called a materialized value of the graph. So let's think of it like this. Like, think of a graph. It is some kind of a blueprint for a stream, but it doesn't do anything until you run it.
Are you sure that you
Sorry. Okay, so let's continue. Running a graph allocates the right resources for the data flow. That means instantiating the actors, allocating the thread pools, sockets, connections, whatever it might be for running a graph. Every resource is transparent, so you don't need to concern yourself with the resources running a graph. It is called a materialized. It is basically known as materializing the graph, and the result of this is called a materialized value. So the materializing graph will involve materializing all the components that compose that graph out of which the graph is made. So first, a component can materialize multiple times. So you can reuse the same component in different graphs. You can run a graph multiple times, but different runs imply different materialization and thus different materialized values. Second, and the most critical thing here is that the materialized values can be anything at all. So if we have a component, it will expose the dematerialized value, and it can be a concrete useful value such as an integer, or a future may be containing a value, or it can be a connection to some other service. It can be an actor. It can not also. It can also be a unit. It can be nothing at all. It can be empty. So, and the materialized value may or may not have any connection at all to the actual elements that go through that particular Akka stream. So, moving forward, the next second point is operation, fusion, and async boundaries. So, the Akka stream components are fused. By fused, we mean that they run with the same actor. Akka stream operators, they are fused together and execute sequentially by default. This avoids the overhead of events crossing asynchronous boundaries, but it limits the flow to execute at most one operator at any given time. So we can introduce async boundaries where components will run on different actors. Also, this will help us, there's an advantage of this, it will help us yield better throughput when operations are time consuming. So this is the best. It can be used, it has the most advantage when individual operations are expensive, and it should be avoided when the operations are comparable with a message pass. So it is a kind of situations when async boundaries work the best when individual operations are expensive. So you want to make them run in parallel but you want to avoid async boundaries and stick to operator fusion when operations are comparable with the message. So the next point and final point is the back pressure. So this is one of the most important features of the streams. So let's see what back pressure is all about. It is one of the fundamental features of reactive streams and of course Akka streams as well. And it's based on a few key ideas. First is that the elements flow as a response to demand from the consumers. So when the consumers are actually the one who trigger the flow of the elements through a particular stream. So if we have a simple stream composed of a source, a flow, and a sink, elements don't flow through the stream unless there is a demand from that particular sink, which I've already seen what sink basically means. So the sink will issue the demand from upstream, and the flow in between will also issue the demand from the source. And after that, the elements will start flowing. Now, back pressure is all about the synchronization of speed in between these asynchronous components. So in the case that the consumers are fast, then all is well in the stream's length because the consumers are processing the elements as soon as they are available. But what if the consumers are slow? So in that case, then you have a problem because the upstream is producing elements faster than the consumer is able to process them. So in that case, we have a special protocol which will get kicked in, which the consumer will send a single signal upstream to slow it down. So if the sink is very slow, it will send a signal upstream for the producer to slow down. If the flow is unable to comply, it will also send a signal upstream, which will limit the rate of production of the elements at the source. So if the source slows down, then the incoming rate of elements at the flow will also slow down, which will also slow down the flow of the entire stream. If the consumer sends more demand, then the rate of the stream may increase. Again, this protocol is known as the back pressure, and it's transparent to us, although we can control it. So moving forward, we have graph DSL. In Akka Streams, computation graphs are not expressed using a fluent DSL like linear computations are. Instead, they are written in a more graph resembling DSL, which aims to make translating graph drawings to and from the code simpler. So DSL basically stands for domain specific language. In Akka Streams, the graph DSL is a powerful tool for building complex stream processing topologies. It allows you to define and connect stream processing stages in a more flexible and expressive manner. So the graph DSL, it provides a higher level of abstraction for constructing stream processing graphs using a visual and intuitive syntax. So instead of using the traditional linear chaining of stages with operators like map or filter, the graph DSL, it allows you to define a graph of interconnected processing stages using various graph building blocks. So we have some of the basic components. Key components of this are shapes, operations, and connections. So shapes basically define the input and output ports of the processing stages. The most common shape is the flow shape, which has one input port and one output port. But there are also other shapes like source shape, sink shape, uniform fan shape, uniform fan out shape, which will be going through in the further slides. And also they have different number of input and output ports. Then we have operations. The operations represent the processing stage in the graph. They can be sources of flows. Operations have input ports and output ports that connect them to other stages. Then finally, we have connections. They're used to connect the output ports of one operation to the input ports of another operations. Connections are created using the operator, which represents the flow of data from one operation to another. So using the graph DSL, you can create complex stream processing topologies with branching, merging, and feedback loops. It allows you to express more sophisticated data processing scenarios that cannot be easily represented using the linear chaining approach. So in Akka Streams graph DSL, we have two concepts known as the fan in and the fan out. The other concepts used to describe basically the behavior of stages that merge or split the streams within a stream processing graph. So first, let's go through fan out. Fan out operation basically splits a single input stream into multiple output streams. They take a stream of data and distribute it among multiple destinations. In the graph DSL, the uniform fan out shape is a shape that represents a fan out stage with multiple output ports and a single input port. So some examples of fan out operations are broadcast, balance. So broadcast basically distributes the input stream to multiple output streams, emitting each element to all output streams. Balance basically it distributes the input stream to a dynamically changing set of output streams, aiming for an equal distribution of elements. We also have one more, which is partition. It splits the input stream into multiple output streams based on a given predicate or a particular function. Second, we have fan-in. Fan-in operations merge multiple input streams into a single output stream, which is opposite of fan-out. They basically take data from multiple sources and combine them into a single stream. In the graph DSL, the uniform fan-in shape is the shape that represents a fan-in stage with multiple input ports and a single output port. So the some examples of fan-in operations are merge, zip, and concat. Merge, it basically merges the multiple input streams into a single output stream. It emits elements from any of the input streams as soon as they become available. Zip or zip width, it combines corresponding elements from multiple input streams into the tuples. It emits a tuple when all the input streams have provided an element. Then finally, we have concat, which concatenates multiple input streams into a single output stream. It first emits all the elements from the first input stream, then from the second, and so on, which waits for every single input to finish before picking up the next one. Now, both these operations, the fan-in and the fan-out, they are essential building blocks in Akka Streams graph DSL, domain-specific language. They allow you to merge and split the streams, enabling various complex stream processing scenarios and enabling the construction. And these stand-in and stand-out components, along with sinks and flow and source, they can be used to design graphs of arbitrary dimension and complexity. Moving forward, we have integrating the Akka streams with actors. Actors can be inserted at any point inside the Akka streams, and they act as a source of elements, as a destination of elements, and even inside the middle of the Akka stream. We can make our stream interact with plain actors, and actors can act as a fellow by calling the ask method on flow, which operates based on the ask pattern on actors and on features behind the scenes. If you want to connect a source to one of these flows, we can use the ask method directly on a source, which is equivalent with an ask-based flow. We can also use actors as a source of message and elements inside a stream by calling source actor there. And in that case, the actor is returned as a materialized value, which we have already seen in the previous slide. What is a materialized value? We can also make actors act as a sink, as a destination of messages. And in that case, the technique is a bit more basically evolved, because we need to support some life cycle messages that the actor needs to interact with the rest of the stream. So moving forward, we have fault tolerance and error handling, which is a major important part of the Akka streams. So first we have logging. Logging is super useful during development. It is sometimes helpful to see what basically happens in a particular section of a stream. We also in day-to-day life while coding, we use loggers as well. So the simplest solution is to use a map operation and use println to print the elements received into the console. While this recipe is simple, it is often suitable for a quick debug session, which we all use. Another approach to logging is to use the log operation. This approach gives you more fine-grained control of logging levels for elements flowing through the stream, finish, and basically if there's a failure in one of the streams. So when an operation in a stream fails, this will normally lead to the entire stream being turned down. Each of the operators downstream get informed about the failure, and each upstream operation sees a cancellation. In many cases, you want to avoid complete stream failure. This can be done in a few different ways. First is the recover. Recover is basically to emit a final element when complete the stream normally on upstream failure. It allows you to emit a final element and then complete the stream on an upstream failure. Deciding which exception should be recovered is done through a partial function. If an exception does not have a matching case, then the stream is failed. Recovering can be useful if you want to gracefully complete a stream on failure while letting the downstream know that there was a failure. Throwing an exception inside the recover will be logged on error level automatically. Then the second, we have recover with reprise. So to create a new upstream and start consuming from that on failure, we use recover with reprise. It allows you to put a new upstream in place of the failed one, recovering the stream failures up to a specified maximum number of times. Deciding which exceptions should be recovered is done through a partial function. If we don't have a matching case, then the stream is failed. And then we also have restarting the sections of the stream after the backup. Akka streams provide restart source, restart sync, and restart flow for implementing the exponential backup supervision strategy. Starting an operator again when it fails or completes each time the growing time delay between the restarts. This pattern is useful when the operator fails or completes because some external resource is not available and we need to get it some time to start up again. Using a supervision strategy for operators that support it, the error handling strategies are inspired basically by the active supervision strategies. The semantics have been adapted to the domain of stream processing. The most important difference is that the supervision is not automatically applied to the stream operations, but instead something that each operator has to implement explicitly. So for many operators, it may not even make sense to implement support for supervision strategies. This is true for operators connecting to external technologies, where, for example, a failed connection will likely still fail if a new connection is tried immediately. So there's a time delay between the restarts. So for operators that do implement the supervision, the strategies for how to handle the exceptions from processing stream elements can be selected when materializing the stream through the use of attribute. There are three ways to handle the exception from application code. We have stop, resume, and the restart. Stop basically the stream is completed with failure. Resume basically means the element is dropped and the stream continues. Restart basically means the element is dropped and the stream continues after restarting the operator. Restarting an operator means that any accumulated state is cleared. This is typically performed by creating new instances of the operator. So by default, the stopping strategy is used for all the exceptions. That is when the stream will be completed with failure, an exception is thrown. So in addition to these built-in tools for error handling, a common pattern is to wrap the stream inside an actor and have the actor restart the entire stream on failure. So this is all about fault tolerance and error handling. So moving forward, we have a demo which Anshika would be conducting.
So for the demo of whatever we have gone through till now, so I have created a project on Akka Streams. So for that, I have created the project on Scala. So using SBT, I have created a build.sbt file in which there are two dependencies that have been added. One is for Akka Actors and another one is for Akka Streams. So as this is an Akka Stream project, so the Akka Stream dependency is required, and as Akka Streams is kind of a build on Akka Actors only, so we need the Akka Actor also, and we'll be showing this in the demo later on. So first, let's start with the basics of Akka. So we will be starting. Let's talk about streams. So there are two main things. So basically in these streams, there are three things: source, sinks, and flow. But there are two main things: source and sink, that are mandatory part, and another one is flow that can be optional also. So source is basically the data producing. It is at the data producing end, and the sink is basically at the data receiving end. So here, as you can see, I have created an active system and then adding a materializer here. I have created a data here. This data can be anything and can be produced from any end, like database, data warehouse, data lakes, or anywhere it can be. But for example, to demo here, I have created a list and val data and list, and it contains some strings. So in this, we have a data, and here I've created a source using the source keyword. And in this, I have passed the data. So this, like this, we can create a source in Akka Streams. And then moving forward, I have created a sink also. In this, we have sink, and we have provided an operation on the sink, like sink.forEach, and the processing will be based on the strings, and we will be printing it. So here you can see that I have created source and sink, and we'll be connecting it later on here and running it, and there is no flow that I have added. So flow can be optional, and Akka Streams provide the feature that we can perform the operations on source also and sink also as per our requirement. So here, if I will uncomment this part, to connect the source and sink, what we need to do is source, and then we have to pass the data to sink. Then we will be adding the to sink, and to run this connection, we will be using the run method. So I'll be running this, and you can see that whatever data we had, that is printed here in the sink. Okay, so this is the very simple example of a source and sink connection. Then moving forward, we have to transform the data between the source and sink. Then what we have to do is we have to use flow. Okay, so there are many examples you can do. So I am adding here two basic examples. One is transform one, that is flow, and the operation will be on the string and adding the map, and it will convert all the data that we will be receiving to the uppercase. And the transformation to it, what it will be doing here, it will be concatenating basically all the elements that we will be receiving. So I have added the multiple examples. Here is source. Okay, so above we saw that how we can connect the source and sink and then run it. Now we have to connect the source and sink using the flow. So what we will be doing is that we will be adding source, and through flow we have to add. So via this transformation one I have to add. So transform one and then to sink and then run. So what it will be do, it will source will produce the data, transformation will be done in the flow via transformation one, and the data will be passed to sink and then it will be run. So if I'll run this, what will happen? All the data that we have received, that is converted in uppercase here. So this is the transformation that is processed. Now, if I see for the second example, so it has connected all the data that we have received as per the transformation tool. And similar way, I have in the third example, what I have done is I have connected all both the flow. So basically, I am performing two different transformation on a single data stream. So what is happening here is that we are receiving the data from the source, and from via transformation one, what will happen is first this transformation will happen, this flow will happen, converting it all to the uppercase, and then this transformation 2 will happen on top of that what is happened in this, and then it will be passed through sync and then we'll run it. So let's see what happens. So see, both the operations that we have seen above, like this in example 1 and example 2, we can see the combined result in example 3 that you have shown, because we have combined both the transformation here. Now, moving forward, we have multiple examples on flow operation. For example, I have created here a source in, that is source is taking integers from 1 to 100. Then I have created a flow that is taking integer and printing it all the numbers integers on the basis of divisibility of 7. Then I have done the map on that flow, and we are multiplying it by 2. And further, what we are doing is we are creating the sum of whatever the elements that we have received, and in this thing we are printing each element that we have received. So for the connection part, I have created a source integer. This source integer, it will go through filter flow. It will filter the elements based on the divisibility of 7. Then it will map all the elements, multiplying it by 2, and then it will add all the elements, and then it will pass to the sync, and sync what it will do, it will print the result. So let's see what happens. So here you can see that we have received the output as 1470 as a result of this stream. Okay. Then moving forward, we have some advanced methods also. So here I have created a new sync, which is sync.head integer. So also one more thing to add on, there are multiple operations that you can perform on the sync and source as well. So if you see here, let me show an example. Sync dot, like for example, I have performed the operation for each above before in the code base. Then I have ignore what it will be doing, that it will be without performing any operation on the sync. The outcome that it will be receiving, it will be simply receiving that outcome only, and it will not perform any operation on it. Then similarly, we have head, fold, from graph, actor graph, and there are multiple operations that can be performed. So there are number of them, you can see. And similarly, we have them for the source as well. So here earlier I have used the method as for each on the sync, and now I am using it sync.head. Now what I am doing is I am using the source integer that I have created, that is taking number from 1 to 100. I am adding the filter flow on it, that will be taking as per the divisibility of 7. And then it will be adding all the integers, and then it will be returning the new sync on the head, and it will print in later on, because we need to see the outcome of what we are receiving. So here I am printing the result also. And also I have used the run with method, which is run with is basically, earlier you can see I have used only run method, which was synchronous. But this run with method is asynchronous, and it will be returning the outcome in the future. So I am using the map and then printing the outcome of what we are receiving here. So let's see. So here we are receiving 1470. So the outcome is same for both. And also one more thing to show, because I have used the run with method, so and use the map and did the println to return the outcome of the stream. Similarly, I can use on complete also, because the outcome is in future. So we will be using the on complete, and a non complete method, as we know, there are two cases that we can handle. One is for success case and another is for failure case. So in success case, what we are doing is we are printing the value, operation completed with value. And in the failure case, we are returning the exception here. So let's run it. So we got the output as operation completed with 1470. Then moving forward, moving forward, we have source integer, that the source that we have created, and on that source we are applying the method run fold. Like we have seen run method, we have seen run with, now we are seeing run fold, and we are performing an operation to submit. Okay. So we have created the run fold and we have created the source here. Then we have source. Then we have source integer, run reduce and do the summation and fold. Now fold flow, what it will be doing, it will be running with source integer and sync integer. Sync integer was this, it will print all the elements. And so fold flow will take, fold flow is this. There are many ways that we can connect and perform the transformations and write the code in the sync, and with this using the sync, source and flow. So it is another example. So here we have added the flow first, and then we are running with source integer and sync integer. And then we have sync integer run with source integer. So let's see, let's print the output. Okay. So we can see here that we have output. So for this example, sync integer run with source integer was 1 to 100, and sync integer was printing each element that it has received. So it has printed all the elements that it has received here. And 5050 is printed with the fold flow, and the source integer sync it. So this is an example of simple Akka streams and how we can perform it. And also one more concept that we have learned that Purva already mentioned about, that there are times when the data that is produced, the speed is very high, and the producing data is very high at very high speed, but at the receiving end the processing is really very slow. So at that time the data get collected in the pipeline, and so to avoid any hurdles we use the concept of back pressure. So at that time the back pressure comes into picture, and what we do is we provide the pressure in the upstream motion in the upstream direction, as Purva already mentioned that whenever the flow is in the towards the source direction, then it is in upstream direction. So then we apply the concept of back pressure there, and to run the pipeline and the stream smoothly, we provide the back pressure in upstream, so that the at both ends the speed of both the producing of data and receiving of data can be balanced, and the stream and pipeline can run smooth. Now moving forward, we can see about the DSL. So so here in the basics we have seen that we have a very minimal amount of data. But now if we have the data in bulk and we need to process all the data in parallelly or compute the data parallelly and provide the result as per our requirement, so then the DSL comes into picture. So here also I have created an active system, created a materializer, added data in the same way, and created the source as we have seen in example. Source 1 is also the same as source int that it was. Then operation 1, it is converting it all to lowercase. Operation 2 is float, converting it all to uppercase, and operation 3 is all getting the length of it. And sync is basically printing all the elements. Now let's learn about DSL graph. So when you will see in the stream basic, I'll show one thing. If I will create a val connector, for example, here, and remove this run method from here. Okay. So what if I will or annotate this? So if I will annotate it, then you can see it is a runnable graph that we have created. This source.toSync, this is already a runnable graph that we are creating it. Okay. So in the DSL, we will be running. So we will be creating a runnable graph here. So first we'll be creating a runnable graph, and then from graph we will be creating a graph DSL. So using that graph DSL.create, we will be creating, because we want to run the we have a data in bulk and we want to run all that in parallel. So we'll be using the graph DSL, and then we have to build the graph DSL. We have to build the DSL. So there are multiple implicits that are required. So for that, we have used this implicit Akka Streams Scala DSL graph DSL implicits import, and it will be importing all the implicits that are required for generating a graph DSL. So here, what I'm doing is I'm creating a broadcaster, because for example we have so a single source and we have to broadcast it into multiple outputs. For example, here 2 outputs, or we have to perform 2 operations on it. So we have to broadcast the data. So now using the broadcaster, we are creating a builder, and in builder we are adding the broadcaster, and we have the output port as 2 here, because we have to perform 2 operations. Then what we will be doing it later on, we will be zipping it. So we will be doing builder.add and zip on the zip the data, because we have 2 input from here. We will be receiving broadcaster, we will be receiving 2 input. So we have 2 types provided in the zip. So now we have created the broadcaster, we have the source already. So from the source we are passing the data to broadcaster. Now broadcaster, what it will be doing, because we have 2 output ports, so let's see what we have to do with first output port. So we are doing dot out, and 0 is the first output port and 1 is the second output port. Then we will perform operation 1 on it and zip it in 0 output 0 port, and similar way we have to do it for the second output port also. Now once we have zipped in, now we are doing the zip out and into sync. We are using the in when we have to pass inside the data. That is, we have to produce the data, and out when we have to receive the data. So at for example, after performing the operation, we have to receive producing the data here. So it is zip, and we are in the sync, we are receiving the data. So here we are using the zip.out. Now we have created the graph DSL here. So we have to use the closed shape here, because it is kind of an identification that we have done with our graph creation, and now it is complete. And then we have to, as we used for here also, to run the runnable graph, we were using the run command, run method here. So similar way we have to do it for graph also, graph.run. Okay, so this is one of the example of runnable graph, you can say. Then this was all done on the graph. Now we have, if we have to modify the source, then what we will be doing is that earlier you saw that we are doing it on the runnable graph. Now we will be doing it on the source. Then, so we have here source.from graph. Similarly, we will be creating the graph DSL builder, and we have to now, so now what is happening is that we are receiving single data. We have receiving the multiple data, and we have to perform a single operation on that. Then we have to perform this source.from graph, because we have to concatenate now. So we are creating the concatenator here. So on the builder, we are adding the concatenate, and input ports are 2. So we have 2 different sources here, source and now concatenate now, and source 1 concatenate now. And since we have created the source graph here, so we will be doing like the runnable graph, we have used the closed graph, closed shape. Now in the source, we will be using the source shape, and then concatenate out. And in this similar way, we have used in above, we are using the graph.run. Now here we'll be using modified source.toSync.run, because this was the source. This is the source that we are modifying. Now we have to transform this data to somewhere. So that will be in the sync. So we will be creating it .toSync and then run. Now, as we have seen it for graph and for source, similarly we have for sync also. We have created 2 different syncs here, and in this we are creating a modified sync from graph DSL create, and then from broadcast we have to create a broadcast, and from broadcaster we are receiving the sync, receiving the data in 2 different syncs. So from broadcast 1, we have only single broadcast but multiple syncs. So we are transforming into the multiple sync, and earlier we have used source shape for modifying the source, and now we will be using the sync shape and broadcast.in. And similarly, source was the same, source.to modified sync, and then run. So in this way, we have seen that we have used the runnable graph, source, and sync. We have modified all this and used our DSL in this. Now we have seen the integration. We have learned about the integration of actors in the Akka stream. So we have created an actor here, that is actor runner, and defined a receive method here, and which is handling 3 of the cases. First, it is receiving the string and integer and else case. So when it will receive the string, it will return the length of the string. If it will receive the integer, it will multiply both the integers and return to the sender, and else it will throw the null pointer exception. So we can see we have created an actor system here and a materializer here, and an actor also, actor ref, using the same actor system with actor run case class. Now we have created a data and the source. In source, we have passed the data in the similar, that is a list of string, and in the sync, what we are doing is we are printing each element that is received in the sync. Now, if now for the flow part, we can see that we have used the operation of flow, string, and .ask method. As you all know that we have ask and tell. There are mainly two types of message passing ways that we can use for the actors. So here we are using the ask method, and since we are using the ask, so we have to provide the timeout also on how much we can wait on the response from the sender. So here we have used the 2 seconds, and for flow we have used the ask, and then also pass the actor, to which actor it will use the ask operation for. And similarly, now we have source via new flow to sync and run. If this is the same as we have seen earlier, from source, then transformation, and then to the sync, and then run. So this is how the actors connect to the the Akka streams, and this is a very basic example on the flow part, but we can use it in multiple ways also. One last thing is that we can also use fault tolerance. So for fault tolerance, another actor system is created, actor materializer is added, data is created, and in the source we have passed that data, and in the flow what we have done is that if the data that is received in the flow is of size less than 6, then it will be okay, and if not, then it will throw a null pointer exception, and in sync it will print each element. Now what is happening is that in the source at the source we are receiving the data, then via flow and then sync and then run. So when it will receive Nolda's, hashtag or Anshika like this, it will fail. At that point it will throw null pointer exception, and else case it will pass. So now creating another flow, what we can do, we can recover it. So when this flow will fail, at that time we can use the recover and handling two cases here. That one is null pointer exception, one is wildcard case. Handling null pointer, we will return the try again, and handling the wildcard, we will say try again another. So it is an example of how we can handle this exception here. Now we can see another example is that we have another connector created here, that source via new flow one. This new flow one, what it is doing is that it is providing the recover on the flow and then to sync and run. So in this case, we have handled the error exception because the null pointer exception it was throwing earlier, and which would block our system. So this will avoid that blocking and using the recover method. Now we have created another source one. What it is doing, if it is checking if the string that we are receiving contains k or not. If not, then it will throw a null pointer exception. If yes, then it will pass. So here we have used recover with retries method. So what it will do in the source one, it will recover with retry 2 times, and in else what it will do, it will perform the data on the source, and via flow new one, it will pass to sync and then run. And another method also, another example also of error handling can be with attributes. What we have done, as Purva already mentioned, that we have multiple supervision strategies also, as you know, for actor handling. We define multiple strategies. In the same way, we can do it for Akka streams also. So here we have done with attributes, actor attributes and supervision strategy we have applied here. So it is handling the null pointer exception. When it will receive the null pointer exception, it will resume from there. But in all the other cases, it will restart and then will flow and then sync and will run. So I think I covered most of the topics that were discussed in the slides earlier. So that was all from my end. Thank you.
So guys, do we have any questions related to this session? Any questions? Okay, no problem. So I think we can wrap up the call. Thank you for sharing such an amazing session, Purva and Anshika. And if you guys have any further queries, feel free to connect with Anshika and Purva. I'm sure they'll be happy to help you with your queries. And have a good day, guys. Thank you. Thank you for joining in.